So this is an improvised talk. So don't blame it to me, just on Hugo. Don't take the blame. So anyway, I'm going to present a polymorphic virus I made 3 years ago. So I'm going to present the features of this virus. So it's a polymorphic virus. It's pretty infectious. It has entry-point obscuring techniques, which is basically the virus is not changing the headers, like the field, the address of the entry point in the headers, and rather than this, it patches the original application to redirect to a few chunks of obfuscation before actually executing the actual virus entry point. So it has obfuscated layers using a shitload of junk instructions and different decryption operations. And the thing is, back then there was a bug in VMware 5 with one instruction, so the virus was actually crashing on VMware 5. So this was a pain in the ass. So it was using the VRW instruction. And this instruction takes a register as a parameter, and obviously this was all random. So it doesn't crash on the real computer, but it crashes on the VMware. So tracing through the layers was very boring and slow because they were pretty big, and you don't actually know how many layers the virus created because it's random. So what I did is I'm a lazy person, so I try to find a pattern, and most viruses and packers or anything doing encryptions usually have a pattern that you can locate and exploit. So in this one, fortunately, it's really simple. It's a CMP and 2 random registers followed by a GB, but unfortunately there is fake CMP2 followed by a GB, but those fakes one are actually jumping very close to their EIP, whereas the real ones are jumping very far because the layers are pretty big, so you can actually use a pattern from this. So I made an early script to automate the layer tracing, so I could make some coffee while it tries for me. So this is an example, VRWAX, the instruction crashing the virus on the VM. So the good thing with OliScript or any scripting language for debugger is you can control the debugger and automate debugging sessions. So it's very useful to script in packers or any tracer for decrypting protections or viruses or anything like this. So I wrote a dodgy virus tracer. So what it does is single step through the wall layers only once per layers. It removes the anti-VM opcodes and it locates the end of the layers using some pattern matching shitty technique. And so you put a breakpoint after the GB and you resume executions. You only trace once per layer, otherwise it will take forever. But the thing is, since the anti-VM use random registers, I had to come up with some ways to identify them, because otherwise I would have a lot of patterns. So I was actually applying a mask to the opcodes, so I could identify any VR with any register. And so you have to know where you are going to stop the tracing through the layers. So most viruses use a call followed by a pop to calculate a delta offset. It's used in shellcodes and packers as well, just to know where your data is, because you don't know where the virus is going to be in memory in advance. So anyway, I assume that eventually the virus is going to get a delta offset. So I did some lame pattern matching, but it worked. So I'm going to do a demonstration now. So I just first try to do it like manually. So you are inside the code section, and so this is a real entry point of the host application. There is some junk instructions injected through inside it. So you get a lot of redirections until you find the actual start of the virus in the last section. So if you just right through it. Okay, on this one, this is virtual PC, VMware 6, so it doesn't crash anymore, but it did back then. So you see here, this is a fake loop to avoid easy pattern matching, but it's actually very easy to identify this is a fake one. So anyway, if you trace through it, this is still the first layer. I didn't even yet reach the end of the layer. So anyway, it takes too much time. So as you can see, while it's tracing through it, it's knowing every anti-VM instruction for me. And so it does all the hard work. So it's not really generic, but it works on every instance of the layers. So it's only tracing once per layer. And you can have 26 layers, so it takes a lot of time to do it manually. It's a bit slow, but since I only worked on my slide for 20 minutes, it's good to have some slow demo. Again, blame it to Hugo. So usually I do some coffee while it tries for me. So imagine if you have to do that manually. So it's find the end of the loop pattern, put a breakpoint after it, executes the virus, so it stops on the breakpoint and start tracing again the next layer. So you only trace the layer once, and then you execute the application, so it does all the iteration for you. It's a lot faster, but still it's pretty slow. Hopefully it's done soon. All right, there we go. So the virus is actually decrypted in memory now. We can dump it and analyze it statically with IDA. So if you look here, you see the call, pop, sub, stuff. This is a delta offset. This is what I use for the stopping condition. All right. So now the virus is decrypted in memory. You can start the hard work. So you've done the process on disk, and you can start static analysis with IDA. Or you can also debug your virus without going through the layers anymore. So now it's a lot faster. So the virus is using delta offset, which makes static analysis a bit harder. So in order to read code easily in IDA, what you can do is load the file manually. There's an option in IDA, you will press manual load, and you can actually subtract the delta offset from the image base, and the virus code is going to be a lot easier because you can rename variables and everything, so you don't have to use an IDC script or structure or whatsoever. But the rest of the host application is going to be relocated, so you cannot analyze it anymore, but we are interested in the virus anyway. So you just manual load, and you enter the image base as an X address, minus an X value for the delta offset. You calculate it from the call pop sub register. So now the file is loaded nicely, and it's a lot easier to analyze. All right, next slide. Don't use this technique. I made the screenshot a long time ago, so I didn't have enough time during lunch. So again, complain to Hugo. This is the actual code doing the. I don't know if you can see anything, but this is a call pop sub EBP, and to calculate the delta offset. So most viruses use this kind of code. Then the next thing you actually encounter in the virus is, so I told you the entry point has been patched, and it redirects execution to a few chunks of code with obfuscation in the polymorphic chunks to avoid easy detection. So the first thing it does is it patch backs everything inside the host application. So you have some sort of structure with the removed bytes and the pointer to the original location and the number of bytes overwrite, and as well the number of chunks removed. And every infected binaries have a different number of chunks, obviously. Then the next thing you encounter is a home get proc address kind of function, because the virus has no EAT. So it's actually doing some dynamic API resolution. This is pretty standard code, and it's easy to analyze. So anyway, then you have some lame anti-debugging techniques. It makes an exceptions to throw like lame reverser off. Anyway, so there is an exception, and it generates an exception and then do an accept and keep resuming the application. Then there is very lame anti-debugging techniques. Everyone knows it. It's access to the PEB. I don't know why, but those guys are doing 100,000 loop iteration and try to detect the debugger. It's useless. It's only reading a byte. So maybe it's just to throw off emulator because they are going to stop execution at some point. But anyway, then an old one, it's using melt ice, which is soft ice detection. Also, this is useless because the latest version of soft ice is not detectable with this. Anyway, then you have the infection, the actual file infection code. So what it does is it opens files, then maps them with create file mapping and map your file. And then it does some checks on the file. First thing it does is, so it does a push MZ on the stack and pop it back. So it looks if there is a MZ header. If there is not, it's not a file that it can infect. Then it checks for some marker, some random bytes at some useless field in the P header, the MZ header actually. So most viruses use markers to know if the file is already infected or not, so they don't over-infect the file. Then the next thing it does is it gets the address of the offset of the P header, and if it's above 200x, it just doesn't infect the file. So it's probably to avoid some crashes or something on fancy files. Then it checks for PE, which is the PE marker for the PE files. And if all those checks pass, it's going to try to infect the application. So on this slide, I don't know if you can see anything, but on this slide, you can see the sections manipulations. So the code is, the virus is appending itself at the end of the host program. Just before that, there is a call to a function which is going to remove chunks of code from the host application and generate polymorphic layers too before actually modifying the section of the last the last section. So what it does, it plays with section alignment, so the file is still well aligned, even if the virus is at the end of it. And so you do many things like update the row size of the section and virtual size, and do many things to align the file. Then you put the infection marker, the one we just saw before, to mark the file as infected. Okay, so this was simple stuff. So now, if you want to analyze a polymorphic engine, a few things you have to know before you start is polymorphic engines use pseudo-random number generator because they want to do some randomness. And most of virus writers are very lazy, so you usually use the same kind of code. And there is some MD instructions to generate a byte or a word or a D word, which is a store instruction. So a lot of polymorphic engine actually use this kind of thing. Then you have loops to generate more than one layer. So an helpful thing to have is the Intel Opcode documentation to identify which instruction is actually assembled by the engine, because you only see the bytes, the opcode, and you don't know them by, well, I used to, but I'm getting old. So anyway, it makes things easier and quicker. So this is actually the start of the polymorphic generator. So the first thing it does, it gets a number between 0 and 26, which is the number of layers it's going to generate inside the virus. If it's 0, then it tries to get a new number. So the one in the example, the demonstration was only 16 layers, so it could have 26, so it's even slower. Then it called a polymorphic generator subfunction. So this is a wrapper around the pseudo-random number generator function. So this is just a function to generate a number between 0 and the parameter. And this is the actual pseudo-random number generator. And it's easy to identify because usually you have some instructions like RDTSC and then some fancy calculation and sometimes using a famous constant in the pseudo-random number generator. And then it does many things and start to actually write the layers and everything. So in this one you can see the delta offset generation. So I don't know if you see anything, but there is a move AL E8, which is the opcode for a call. Then it's XOR EAX, so there is a new D word, and store it after the E8, which is a call next instruction. Then it generates a random register for the pop. And then it generates a lot of junk instructions. So every opcode generation is using the same thing, move AL, the opcode bytes, and store it. And they do that for every assembly instruction they want to generate in the engine. So for instance, so I told you the end of the loop was a CMP reg 3232 and followed by GB. So a CMP with 2 registers. So opcode is 3B. So you can see move AL 3B, and then you store the byte. Then it does some use a random value to get the register for the parameter of the CMP. So it's storing the CMP. Then it will move AX 820F, which is the opcodes for a long GB, the one used by the loop. And then it will calculate where it's going to jump eventually. So it depends on the number of jumps it's going to generate. So again, it's calling the generate big trash block function. Also, there is very simple encryption, but it's as the virus create layers, it's auto-modify itself and patch itself to subtraction, XOR, addition, or anything like this. So the junk code engine is actually very basic. It calls, it gets a random number between 0 and 22. Then it uses as an index in an array of opcodes, like this. So every of these lines is actually an opcode for 1 byte instruction. So you pick one randomly and store it and do it again. This is for 1 byte chunk, but for bigger instruction, you just have handlers for any kind of instruction you want to generate. So yeah, I know it's boring assembly code. So you just put the opcode in the register and do some magic and assemble it. This one for the neg register, because you can do like neg register, and everything is random. So I guess I'm done. Do you have any questions? No, thanks.